Hello guys, welcome to SpectroTutor. Well, we have a lot of signals today and we need to deal with all of them, but don't worry about it. So this is Parsa, and in the first video I'm glad to give you a brief explanation of how things are going to go here. This channel is all about learning how to interpret the spectra, IR, NMR, mass, and more, and using them to uncover the structures of compounds. But we do that usually, but we have different types of compounds and different problems, and we will deal with all of them together. That's a good part of it. So in our approach, we usually begin with the index of hydrogen deficiency, IHD, or you might see in other papers, documents, or books, UI, which stands for unsaturation index, but they share the same concept, and they're the same actually. So that gives us the first clue about the compound's degree of unsaturation, and that assists us so much further analyzing the spectra. So it can mainly keep us on the right track and help us find the correct answer and correct structure for our spectrum. So from there, if we have the IR spectrum, that's our starting point. IR is especially useful because it tells us about the functional groups present in the compounds. That's actually all it has to do. So for example, we can see functional groups like a carbonyl, an alcohol, or an aromatic ring will each give distant signals, as you already know probably if you have passed identification of organic compounds course or any kind of spectroscopy courses in university or anywhere else. So once we've gathered this information, we're ready to move to other spectra. Often the next step is H-NMR, which is really helpful, and there we analyze the splitting patterns, chemical shifts, and integrations to piece together the detailed structure, and that's what we're actually doing and looking for. So of course the order can change. Sometimes we don't have the IR spectrum, sometimes we don't have the formula, and instead we only have the mass spectrum, so don't worry about it. We will get through all type of problems and everything in future and in other videos. So in that case, we adapt our method depending on the data available, but the idea remains the same, step by step, narrowing down until we reach the exact molecular structure, and hopefully we do it together. So that's the general way we'll approach compounds in this channel, and let's start by applying this method to our very first example, as you can see here, C3H8O. So like the way we talked about it before, we're going to start by calculating the IHD number, but before calculating the number and the hydrogen deficiency index, I need to explain a little bit that what it tells you. IHD actually tells you the generally and basically tells you the number of hydrogen that your compound does not have. It's a little bit confusing at first, but the whole information that we need to get from IHD number is that whether we have any double bond in our structure or any aromatic group like any phenyl group or even any type of ring like cyclohexane or anything like that. So these will show different numbers, and let me tell you that each double bond shows one hydrogen deficiency number, and if you see, for example, 1, you can expect a CO, like a carbonyl group or anything like that. So the other thing is that each ring also shows 1 number for IHD number, hydrogen deficiency index, and each aromatic group also allocates 4 number to itself. So now let me tell you that how we can calculate the number. The formula is actually, it starts by the number of carbons minus half of the number of hydrogens minus half of the number of halogens plus half of the number of nitrogens plus 1. This plus 1 is really important. You need to keep that in mind for further videos and further analyze that we are going to have in the future. I say that because if you forget to add this 1 to the number that you calculated before, or calculated based on the number of carbons and hydrogens and other elements that you have, so if you forget that, you are going to face many problems and misunderstandings in other steps. So for now, here in the formula that we have right now, we have, let me write it here, we have 3 carbons, we have 8 hydrogens which get divided by 2, and we don't have hopefully any halogens or any nitrogens today, so we're not going to forget that plus 1. It will give the number 0 as the IHD number. So this 0 means that we don't have any double bonds here in our formula, and we don't have any aromatic groups. So we shouldn't be worried about anything very confusing or anything complex. We have just a simple compound here, and we will find the exact structure. So next step, we're going to start with the IR spectrum. We have 2 actually signals, significant signals here. We have others too, but here we call it fingerprint region, so it's not that much informative for us, at least in most cases that we're going to analyze and assess in the future. So these 2 signals that I indicated right now are so much important, and I show it with IMP, but this one has a little bit a different shape. As you can see it's a broad absorption band, which actually shows the presence of hydroxyl group. So hydroxyl groups usually have a broad band in front of the spectrum, and they also appear about 3300. And as we can see here, everything matches the presence of hydroxyl group in our compound. So we can be sure about this. I put a check mark next to it. And here, this absorption band that's which is really sharp, and it's around 3000, usually appears in most compounds that we consider and we analyze, because most of the compounds we have are hydrocarbons, and this signal shows the absorption of the CH-sp3 bond, which we have in most of compounds that we usually analyze. So the information that we're going to take to the next step is that this C3H8O has a hydroxyl group in its structure somewhere. We don't know it yet, but we will understand it after we finish analyzing the H1 NMR spectrum. So here we actually need to start with this signal, as you can see here. Give me a moment. So this signal, as you can see, has been indicated as an exchanger with D2O. This exchanging with D2O shows that this signal shows the proton that is exchangeable, and here we have the hydroxyl group. So we know that the proton here is exchangeable, and we can actually show that this signal we have here, a singlet signal, is for the hydroxyl group. So we can easily now understand that this signal shows the integration of one hydrogen. So based on this, we can copy the integration actually to the other signal we have here, so we can conclude that here we also have another hydrogen. So we have 2 hydrogens, and in the formula we have 8 hydrogens. So this signal, the very early signal that we have in the upfield region, is showing the 6 remaining hydrogens for we don't know yet for what kind of group or what kind of functional group it is. So the 6 hydrogens, we can conclude that it can be 2 methyl groups that shares the similar topicity, because they have actually shown the same signal, not separate signals. You know what I'm saying? So here we can conclude that we have similar methyl groups, and they're actually here in the expanded version. We can see that they show a doublet signal, so we can conclude that they are attached to a CH. And this CH has made both of these methyl groups to show a splitting pattern of doublet. So we show the CH here. Let me make it more cleaner here. So we have a C, we have an H here, and sorry about this. We have 2 methyl groups, and yeah. So we have one more thing here. We spended all our carbons, but we still need to place this hydroxyl group that we have here somewhere. So we don't have anywhere else to put it, so we are going to add it here, attached to our CH that we explained it before. So there will be one more signal. There is no need to actually interpret this signal, but as we know, we have 1 more hydrogens that we didn't talk about it, and this hydrogen shows the signal of a heptat splitting pattern here. And the reason is that we have actually 2 methyl groups, which has 6 protons in total, that makes this hydrogen show the signal of the heptat. So everything makes sense here. And the final structure that we have is 2-propanol. And yeah, so we can say it's actually time to say Spectro done. Hope you found this video informative. If you have any questions, drop them down in the comments, and I'll be sure to answer. Until the next video, have a good one.